Good evening, dear students. Today I am also going to discuss a part of Unit 1 introduction of the subject Electrical and Hybrid Vehicle with the subject code PEEE602A. Myself, Dr. Rajashree Dhua, Assistant Professor, EEE Department. In the previous video, I have given you an idea about the hybrid series electric drivetrain. But as we know that hybrid drivetrains have different configuration. One is the series where there is the electrical coupler. Another is the parallel configuration which is totally dependent upon the mechanical coupler. So today we are going to discuss about the parallel hybrid drivetrain and their configurations. So as we can see from this figure, and I will illustrate each and everything. So what happens is that this is a parallel hybrid drivetrain, and here we are using the word torque coupling, which means the mechanical coupler is somehow enhancing the torque. So, this is basically the schematic of a torque coupling device. So, this is a mechanical torque coupling device, and there are three ports. One is the port 1, another is the port 2, another is the port 3. As we can see, port 1 is unidirectional and both port 2 and port 3 are bidirectional. So figure 4 basically shows the mechanical torque coupling device which has three ports. As mentioned, port 1 is unidirectional input and port 2 and 3 are bidirectional input or output. But both are not input at the same time. Here, input means the energy that is flowing into the device, and output means the energy that flows out of the device. And what happens basically in a hybrid vehicle application, it is designated that the port 1 is connected to the IC engine directly or through some mechanical transmission, while port 2 is connected to the shaft of the electric motor directly or through some mechanical transmission, and port 3 is the port that is directly connected to the driven wheels through some mechanical linkage. So port 3 is directly connected to the wheels. Now, if we consider that there are no such losses and it's an ideal system in the steady state, then what we know, whatever there is the input power, that should be equal to the output power. So the power input to the torque coupler is always equal to the power output. Acha. So we suppose that port 2, that is the port that is connected to the electric motor, is in the propelling mode. So this is considered to be the input, and the power output from the vehicle wheels can be given by this equation. So the equation says that as port 2 is the input and port 1 is the input, so torque and angular speed, that is T1 omega 1 plus torque and angular speed of port 2 T2 omega 2 is equal to the output torque and the angular speed. So torque and angular speed multiplied together basically provides the power. So here in this case, port 1 and port 2 are considered as the input and port 3 is considered as the output. So T3 omega 3 is equal to T1 omega 1 plus T2 omega 2. So this is the ideal case. Now, how the torque coupler equation can be expressed? So here T3 is expressed as K1 T1 plus K2 T2. What are K and K1? K1 and K2 are the structural parameters of the torque coupler, which are basically described by the gear ratio. And once the device design is fixed, these values of K1 and K2, they are also constant. For the torque coupler, T3 is known as the load torque because that is the output one, and T1 and T2 are known as the propelling torques. And this T1 and T2 are independent of each other and they can be independently controlled. However, due to certain constraints, the angular velocities W1, W2 and W3, they are interlinked together and cannot be independently controlled. And so we write W3 is equal to W1 by K1, which is equal to W2 by K2. So they are dependent upon this K1 and K2 values. So they cannot be independently controlled, but the torque can be independently controlled. Now we move on to the different configurations that we can have for a parallel hybrid drivetrain with torque coupling. So this is the drivetrain configurations with torque coupling. So first one, there is this figure, it is known as the two shaft configuration. So this is the engine, the tractive effort and the speed characteristics are shown. This is the motor. So the torque and the angular speed characteristics are shown. These are the batteries. This is the motor controller. And this is transmission 1. This is transmission 2. These are the clutch. And this is the torque coupling device finally connected to the shaft and the drive wheels. So this particular figure, it shows that it's a two shaft configuration in which two transmissions are used. One transmission is placed between the engine and the torque coupler, and the other is placed between the traction motor and the torque coupler. And both this transmission can be single gear or multi gear, depending upon whatever needs we have. So this is having two transmission. Now moving to the next figure, which is known as two shaft configuration but with a single transmission. So what we can see here, this is the engine, this is the motor, this is a motor controller, these are the batteries, and then we have the clutch and the torque coupling device. After the clutch and the torque coupling device, we have transmission. In the transmission, we can see the tractive effort versus velocity for different gear combinations, and these are connected to the drive wheels. So this is known as the two shaft parallel hybrid drivetrain configuration, where the transmission is located between the torque coupling device and the drive shaft. And this particular transmission is known as pre-transmission. In this transmission, what happens is that the transmission basically amplifies the torque of both the IC engine and the electric motor in the same scale. And the design of the gear ratios K1 and K2 in the torque coupler, basically given by the equation 3 that we have already discussed, allows the design of the gear ratios, it will be such that it will allow the electric motor and the engine to reach their maximum speed at the same time. And this type of configuration is found to be relatively suitable when we have a small engine and electric motor in use, where a multi-gear transmission is needed to enhance the tractive effort at low speeds. We need a lot of torque and a good tractive effort basically at low speeds for the propulsion of the particular vehicle. So there, if this particular configuration of pre-transmission with a single transmission is used, it will be very beneficial. Now moving to another configuration. This configuration is known as pre-transmission single shaft torque combination parallel hybrid drivetrain. So this is the engine with this kind of tractive effort versus angular speed. This is the motor. We have the batteries, we have the motor controller, we have the transmission, and then we have the drive shaft and the drive wheels. So this configuration, as we can see, it's one of the simplest and the most compact architecture of the torque coupling parallel hybrid drivetrain. So this is a single shaft configuration where the rotor of the electric motor basically functions as the torque coupler. So the rotor of the electric motor is actually functioning at the torque coupler, and we do not need another separate torque coupling device. And in this case, what we will choose is that K1 will be equal to 1 and K2 will also be equal to 1. And the electric motor can be located either between the engine and the transmission, that is referred to as the pre-transmission, or between the transmission and the final drive, which is referred to as the post-transmission. So this is pre-transmission because the motor is located between the transmission and the drive wheels. And so this is known as the pre-transmission single shaft torque combination. And this is another one. So this is the engine, this is the transmission, this is the motor, these are the batteries, the motor controller, and these are the drive shaft and the drive wheels. So this particular configuration is known as the post transmission single shaft torque combination parallel hybrid drivetrain. So, what happened in the pre-transmission is that the torques of both the engine and the motor are modified by the transmission. However, the engine and the motor are required to have the same speed range. This configuration is usually used in the case of a small motor referred to as a mild hybrid, in which the electric motor functions as the engine starter, an electric generator, and an engine power assistant. However, in the post transmission case that is shown in this figure, the transmission is there before the motor. So this transmission only modifies the engine torque, while the motor directly delivers its torque to the final drive shaft without any modification. So both of these configurations are needed. Why pre-transmission is needed, why post-transmission is needed, that is well explained. Now coming to the next transmission, which is known as separated axle torque combination parallel hybrid drivetrain. So as we can see, there are two drive shaft with two drive wheels. The motor is engaged in one transmission, the engine is engaged in one transmission, so we have separate. So another mode of torque coupling parallel hybrid drivetrain is known as the separated axle architecture, in which one axle is entirely powered by the engine and the other axle, as we can see, is entirely powered by the electric motor. The tractive efforts produced by the two powertrains are added together to the vehicle's axis and the road. The operating principle is actually similar to that of the two shaft configuration, the two shaft one that we have previously seen with the two transmission. And the transmissions for the engine and the electric motor can be single gear or multi gear. The separated axle architecture offers certain advantages for a conventional vehicle. What are the advantages? Is that it basically keeps the original engine and transmission unaltered and adds a electrical transmission system. And basically it's a four wheel drive, because as we can see, one axle is having two wheels and the another axle is having another two wheels, which improves the traction on slippery roads and reduces the tractive effort on a single tire. So the separate axle basically separates the load or distributes the load so that on a single tire, whatever huge tractive effort was falling, that doesn't fall. So this double transmission, tree transmission, post transmission, and separate axle torque combination are the different architectures of a parallel torque coupling hybrid drivetrain that we have in use. And each and every architecture has its own advantages. That's why we have all these different types of architectures.